Hey everyone, this is Daniel. Welcome to another episode of Rock the Code. Today my guest is Peyton Jones. He's one of the heroes of functional programming and a computer scientist in the true sense of the word. He is one of the lead designers and contributors to the Haskell programming language and the Glasgow Haskell compiler, also known as the GAC. He's a fellow of the ACM and of the Royal Society, and he's won all sorts of awards for his wide contributions to programming language design and computer science in general. And he's currently working for Epic Games with the CEO Tim Sweeney on a language called Verse, which brings Haskell concepts and new innovations in programming language design to video games, which is one of the subjects that we cover in this conversation. And we cover Haskell programming language design, design decisions, type classes, strong type systems, AI, and how they can be helped with stronger guarantees among a wide variety of things. And without further ado, please welcome Peyton Jones. Simon, I am thrilled to have you here. Thank you so much for making the time.
That's my pleasure.
Awesome. So while preparing for this conversation, I was thinking of a good place to start, and I landed on type classes because most of this audience is probably going to be familiar with a lot of functional programming concepts and type classes in particular. And you're one of the best people to ask about this because you have so much background with functional programming in general. So how did type classes come along first? And then I'm going to ask a couple of follow-up questions because I am trying to get somewhere.
Okay. It's a nice story, actually. You can find a lot of this written down in the History of Haskell paper. It's a good piece of background about how Haskell developed, quite carefully written paper. So at the time we were designing Haskell, we knew that we wanted to, say, take the equality between two lists or between two trees. And you can only do that for polymorphic types like list of T if T itself admits equality. At that time, the state of the art was just assume that every type has equality. So you have some kind of baked in small set of things like equality, maybe hashing, maybe ordering, which applies to every single type, functions, lists, trees, all of them, with some built-in, runtime system supported capacity, probably based on the representation itself, like pointer comparison. And that was alternative one, not very attractive. Alternative two was what was in ML, which was to have a different kind of type variable. They were called equality types. You wrote them with a little tick, I think. So an equality type admitted equality. So it too was a few built-in things like equality that was that the type system fundamentally knew about. Neither of these was very satisfying to us. Neither of them was very satisfying. And so then Phil Wadler showed up. He sent a message to the Haskell Language Design Committee, which we're wrestling with this at this point, that described type classes almost entirely. That is, in one blow, he said, here's the design, here's what types look like, for all A, EK double arrow A to A, meaning for every type A that satisfies the class EK, the function has type A to A. So it's not for every type A, it has type A to A. It's for every type A such that. So it's like bounded polymorphism. But rather than just describe it as a type system, a type system feature, he also described how it could be implemented by translation into dictionary parsing. So this function, which has type for all A, EK, arrow, blah, it would take as an argument that bound turns into a value argument, a little record of functions about equality. Now, in the case of equality, it's just one of them, namely equality. But if it was for all A num A to A, which might be the type of a function that added one to its argument, then the little record of functions would include a function for adding, a function for multiplying, a function for negating, and so forth. So it was actually rather object-oriented in its way. It was like the V table is being passed as an explicit argument. So the combination of it's a cool type system thing, but it also has a very direct implementation. That was amazing. So even though it was an unforced complication of Haskell, we didn't have to do this, But it was so much more elegant and beautiful than any of the alternatives for doing things that we were struggling with, namely serialization, turn things into strings, equality and ordering, and numerics, right? We didn't really want to have to write f of x equal x plus 1 once for reals, once for floats, once for doubles, once for big arbitrary precision integers, once for finite precision integers. We wanted to write it once and for all. It solved all of those problems at once. And that was, we just thought, we have to do this. We just have to do it. So that was how it was born. The surprising thing that none of us realized at the time is that the whole type class idea turned into a whole research area into its own right. It sort of spawned, multi-parameter type classes and function dependencies and on and on. And indeed, it spawned higher kinded type variables, because when we wanted the monad type class, we needed to have type variables that ranged over type to type. So it was the forcing function for a huge, cornucopia of new stuff that we never dreamt of to begin with. So it was very serendipitous. Firstly, that Phil and his colleague Steve Blott came up with this idea almost out of the blue. Secondly, that the committee grabbed hold of it and said, we have to do this. And then thirdly, that it turned into this rich area. So that's a rather long answer to your question.
This ties very intimately to what I'm about to follow up with, because this is where I'm actually getting at. Type classes, as far as I was able to read, and you seem to confirm that, is it was a solution to an elegance problem that turned into something that branched out and solved a whole class of programming design and programming problems.
Yeah.
And obviously, arriving at the applicatives and the monads and stuff like that. What was the most surprising piece of that cornucopia of things that branched out of type classes? Was it the monad? Was it the applicatives? What were some examples of surprising developments that you didn't anticipate?
I think aside from type classes itself, solved this sort of set of problems that we knew we had, and we knew we could solve them in that way consistently. The thing that the single thing that then leapfrogged into a whole new world that we did not anticipate at all was higher kinded type variables. So we then this didn't force the invention of monads. It was more like the other way around. We knew after a bit, and this was actually a couple of years later than the type classes were born, we invented the IO monad, right? And so we wanted to have put char with type char arrow IO unit, and get char with type IO of char. So this idea of monadic IO, which just had this, but had a fixed built-in type constructor called IO. But we also knew that we wanted lists, and lists were a monad too. So it's natural to say, could we abstract over whether it's a list or a monad? Just as you might say, when I reverse the list of integers and when I reverse the list of characters, I don't want to write two separate functions. I would rather write one function that reverses the list of anything. So reverse has type for all A, list of A to list of A. Now for these monadic kind of computations, we wanted to write functions like that would take, say, a list of M of A and return an M of list of A. That by performing a list of monadic computations, perform the computations in order, one at a time, and return a list of the results. But if you're going to have a function whose type is for all M, for all A, list of MA to M of list of A, then what is this M thing? It's not a type. It's a type constructor.
Yes.
Now, being able to abstract over types was very well established by this point. ML had been doing it for years. Lots of object-oriented languages were picking it up under the language of generics. But being able to abstract over type constructors, that was a whole new thing. There was no difficulty in theory. The real difficulty was to do with type inference. Now, it turns out that you might think, well, abstract over a type constructor, maybe I need lambda in my type lang. language. But as soon as you put lambda in your type language, type inference becomes very hard. So Mark Jones's insight was that we could get 90% of the benefit with 10% of the effort. We could abstract over type constructors, that is, over types of kind star arrow star, could abstract over them without falling into the tar pit of complexity for type inference if we did not add lambda to the type language. Now, that was a huge insight because it was kind of like, oh, if we just refrain from doing this one thing, we can have monads and lists, lists and IO both being instances of the class monad. So the first class that used this higher kinded stuff was the class monad of M, which has an operation like return, whose type is A to MA. Now, I'm making a big deal about this because not many languages have the ability to abstract over type constructors. I believe that Scala sort of does.
Yeah, it does. It does. It has higher kind of types, and you can even do the whole demonstration like the phrase that's half jokingly thrown around, like monads are monoids in the category of endofunctors.
Yeah.
You can express that with Scala because Scala also has type lambdas. Yeah.
So it doesn't have quite as free-ranging. I mean, the constraints type inputs in some ways, but the overall point is that I think Scala and Haskell are pretty unique in having higher kinded type variables, and that is what lets you talk about, even speak about, having monads and applicatives and functors and traversables and that whole zoo of higher order patterns of programming was only made possible by having higher kinded type variables. And without it, you can't even speak the language. So it was amazing. That was really a huge thing. We never, even at the time, we never anticipated just how fertile that particular patch of territory would be.
That is fascinating. Follow-up question to this sort of abstraction. One criticism that is being thrown around, at least in the Scala community and in the functional programming specific subcommunity of Scala, because Scala is so very general, it can also be used in an imperative way and so on and so forth, is that very highly abstracted Scala with type classes and things like that, and higher kinds as well, is that it's very difficult to learn at first, so it has a steep learning curve, and some programmers criticize let's say the productivity of having to write or maintain or fiddle with programs written in that style. Have you seen this sort of pattern emerge in the Haskell community? What do you think about the trade-offs between these very high levels of abstraction and the productivity of the productivity required to produce valuable software?
Well, I think it's the same as the same kind of thing as you might say, would you prefer to write a function that reverses a list of integers and a function that reverses a list of floats? Or would you prefer to write one function?
Right.
Now, you could say that writing two functions is clearer. Right? You just say reverse list of int, reverse list of float. They're two different functions, two different names. It's clear what they do. But it requires a little act of abstraction to say, oh, I can reverse a list of anything, and to think about the type for all A, list of A to list of A. Now, so in a way, maybe we're moving to a high level. Certainly, we're getting a lot more code reuse, and I don't think anybody would question the value of parametric polymorphism. Now, if you then, you could say something similar about higher order functions too, right? So if you can write many things as a fold by passing a higher order function as an argument. But sometimes if you see things written as a fold, you think, blimey, what on earth is that doing, right? You might say it was clearer to write the fold as a new function that's, as it were, the argument to fold is baked into it, right? And instead say fold plus, You just write a function that walks over the list and adds all the elements. Instead of fold multiply, you write a function that walks over a list and multiplies all the elements. Now, so I think what I'm pointing out just is that there is a general trade-off between reuse and abstraction. The key thing is to design abstractions that, as it were, you can think of as a whole. Now, folds you really can think of. They make conceptual sense all by themselves. But you need to get used to them, right? When you first start seeing programs with folds in them, if it's not just, add them all up or multiply them all together, it can be tricky to make sense of. You just need to get used to the power tools. And I think it's the same with these higher-level abstractions of, sequence and traverse. There was an interesting blog post on the Haskell Weekly News just this week about how incredibly useful the traverse type class is. Now, traverse as a fairly a type that you look at it, you think, what on earth is going on? It goes something like T of M of A to M of T of A. We just move the letters around. But it's a fantastically useful and powerful. Once you get used to it, once it becomes part of your vocabulary, you're very productive. Until you get used to it, it's line noise. I remember when I was first looked at Ed Komet's Lens library, or programs that use Lens, the programs seemed like just incomprehensible. You just have to get used to the abstractions. In any language, you can write programs that are just obscure. So the thing about abstractions, you have to use it tastefully. And I'm not saying that, and I certainly wouldn't say that all Haskell or all Scala programs are using abstraction tastefully, but I do think that what we have learned is that there are some abstractions, functor, applicative, traversable, foldable, that have, that fit together well and that keep coming up. They're like patterns that keep reoccurring. So rather than just abstraction for its own sake, it's useful abstractions worth getting used to. So I think, so again, a long answer to your question. There's a tension. We don't always get it right. But there's something good happening here that I think it would be a mistake to just say, we don't care about these kind of abstractions.
How do you define tasteful? This is something that popped up in many conversations that I've had throughout this podcast, this good taste in software engineering or in designing abstractions. In the case of this conversation, how do you develop good intuitions for applying such abstractions tastefully and for figuring out Yes, go ahead.
Yeah, in this case, I just say it's tasteful if it's a pattern that occurs repeatedly in different contexts. So traversable is useful because you see, you can, once you're looking through traversable spectacles, you see it everywhere, right? Like functors are an even easier one. We see maps everywhere. Do you really want to write map on lists and then map on trees and then map on all these other things? No, you'd like to write map once and for all, and it makes sense to abstract that into a type class. Now it's the functor. It's called the functor type class, which has a long, scary name, but it just means things that you can map over. So tasteful in this context means a reusable pattern that occurs a lot.
Interesting. Are there any other concepts that you found while developing Haskell, while developing the GAC, and so on and so forth, that turned out to be much more fruitful than originally planned in the same style as type classes ended up being?
Two things that have turned out to be very widely useful. I'll pick one thing to begin with, and that's higher rank polymorphism. So in ML and indeed in Scala, you can write functions that have type for all A and for all B, I don't know, A to B to list of A to list of B. That's a type of map, right?
Yes.
Now in Haskell, you can write a function. It's rather hard to write this without a whiteboard, but the function has type for all A to A, in parentheses, right arrow, something. So this function takes as its argument a polymorphic function. Now, at first you think, well, what's the big deal? You could always wrap that up in a data structure and pass it. But in practice, we found that this ability to do kind of first-class polymorphism in which the for-alls are not always at the top. They're sometimes nested under arrows. That has been, it feels like it's only a small change, right? You could always simulate it without using it directly by wrapping it up in a new type. So then you'd have to do wrapping and unwrapping all over the place. But hey, if you don't use it very often, that might be enough. So it doesn't add fundamental expressiveness. But I think we found that it's repeatedly useful that people write programs using higher rank polymorphism. They just assume you can do higher rank polymorphism these days. That, again, is hard to conceive of without it. So that's one thing that seemed like a small technical improvement, but that turned out to have pervasive consequences. Another was GADTs, generalized algebraic data types. Not just algebraic data types, but generalized algebraic data types in which you can bind not only existential type variables, but also type classes locally. That gives you something that's very like object-oriented programming, actually. There's a GADT that captures a type class that puts the V table in the data structure alongside the value. That's exactly what an object is. So object-oriented programming is just, GADTs.
Yeah, and GADTs are often modeled using regular O terms. So this is how you usually sell them to more traditional O style programmers.
Yeah, that's right. I should say one other thing about type classes that I've always wondered is about how the OO community. I actually don't know how this plays out in Scala. Is with type classes you can have a function that says num a double arrow for all a num a double arrow int to list of a. Now, what is it? So the idea is this function is going to produce a list of n zeros. So let's call it wombat. So wombat of 3 will produce a list of length 3 that contains zeros. But because of the num a, it could be a list of floats or a list of doubles or a list of matrices, right? But the a, the type, occurs only in the result, not the argument. Right? So usually object-oriented programming, you rely on having an argument that carries a V table that you can, use the methods from. But if the overloaded bit, it has type int arrow list of A, right? So the A is only in the result. You've got nothing you can look at to get a V table out of, right?
That's interesting.
So now I don't quite know how that plays out in Scala, but it's very, very useful.
Yeah, you can express a similar thing with signatures in Scala.
Right. So that's kind of crucial, and it is a bit. So the V table's traveling independently of the values they attach to. I think of it as being like object-oriented programming. The V tables and the values are sort of stuck together, and they travel together, right? In type class programming, the V tables and the values travel around separately. And when they need to talk to each other, that you put them together and they meet and do their thing. But otherwise, they travel completely independently. That's really amazing ability.
I wanted to ask about type systems and the popularity of languages because types are usually sold to programmers as this ability to kill bugs early, but there will appear a tension between fighting with types, if I may use this expressions, versus this sort of productive correctness. And at the same time, some very, dynamically typed languages like JavaScript or Python are hugely popular. So is there something that you see genuinely valuable in dynamically typed languages that statically typed languages didn't get right?
Not anymore, I think. So I'll say several things. One is statically typed languages with not very strong type systems do indeed get in the way. Right, now imagine, take Pascal, which did not have parametric polymorphism. In Pascal, because it was statically typed, if you wanted to reverse a list of integers, you had to write a different function than the list of floats. Bad, right? Actively obstructing what you want to say. In a dynamically typed language, you just write a list reverse function. It'll work on any type list, right? So we solve that by having a more sophisticated type system. Right? So to a large extent, the move towards greater sophistication in type systems makes the type system not get in the way anymore. That's really important, right? I think that's the primary driver, or a primary driver behind people not wanting to use a dynamically typed system is because the type system gets in the way. And I think we can do a lot to make the type system get out of the way by type inference and having sophisticated types. Okay, so that's the first thing.
Okay.
Second thing, as you said, type systems are often sold as, well, we catch type errors early. I think that's completely true. But I would think that an order of magnitude more important is that it allows you to fearlessly refactor and maintain your code 10 years after it has been written and 5 years after all the people who wrote it have left the company. My impression is, and I don't know whether this is justified, but I don't have coal-face experience of maintaining dynamically typed code bases, but my impression is that 5 years after the last person who wrote this code left the company in JavaScript, nobody dares modify that JavaScript anymore, right? It becomes cast in stone, so you end up surrounding it with stuff that, sort of impedance matches the bit that you no longer dare change. Why don't you dare change it? Because even if you have quite a lot of tests, you're still anxious that the changes you make might break something in production.
Something that I'd like to say is that unless you have the types being checked by a sophisticated type system, you still need to have types in your head with a dynamically typed language, because otherwise...
Oh, yeah, everybody has the types in their head, yeah. And the only question is, can you express what's in your head? So that's another sort of more squishy reason is a sophisticated type system lets you write down what you have in your head. A weak type system does not. So my goal with Haskell's type system is to make it as much as possible, make it possible for you to just write down what you have in your head. And therefore, if you can do that, that is amazing, because then, wow, the compiler will check all of your assertions every time it compiles the source code. That's amazing.
Haskell is a quote-unquote lazy language. What are some of the benefits of making it a lazy language versus a strict language?
Oh, well, I'm been on record for, I think, 2 decades to say that laziness has turned out to be... Laziness was Haskell's initial war cry, the initial thing that made it Haskell, and yet it has turned out to be one of its less important features. So the principal benefit of laziness is that it enforces purity. It's very tempting when you write a programming language that is meant to be sort of pure. You could say, oh, well, trust me here, I'm going to say print here, just a little side effect, trust me. But then if I have, I don't know, a function that produces a list, right? If it's a lazy list, but the elements of the list, when forced, may have side effects, then if I have the list print X and then print Y, then when I run the program, when I consume that list, I might evaluate the first element and then the second, or the second and then the first, or neither, or both, or only one of them. So it might print X and then print Y, it might print Y, then print X, or it might print X only, or print Y only, or print neither, right? So that's just unacceptable, unacceptable. So what that means is that in a lazy language, which specifically allows you to, means that the consumer of a data structure decides which things are evaluated, which are not. In a lazy language, it is not okay to have side effects, right? So laziness kept us pure. And that was embarrassing for a long time. We couldn't even do I/O in Haskell for a long time, or we only had very clumsy ways of doing I/O. So that eventually drove us to invent monadic I/O, which has since been very influential in imperative languages, funnily enough.
Yeah, I mean, at least there are dedicated functional programming libraries and mini stacks in Scala. These are the so-called effect systems. One is called Cat's effect, which makes better use of type classes, and one is called ZEO, which wants to be like the ultimate I/O, which is this I/O monad enhanced with some extra types to manage errors and requirements and whatnot. So it has been hugely influential, and it allows you to describe a sort of imperative code by just chaining these programs as values and expressing.
Yeah. But the driver for all of that, I mean, it lets you do I/O in a more expressive way because an I/O performing computation becomes a first-class value, which really nobody had done before, right? But it was just a little fell out as a consequence of the whole monadic I/O story. But the real driver was we wanted to be able to do I/O at all, and in a lazy language that was blooming hard. And so the important thing about laziness is that it forces us to be pure. Purity is actually the important thing. If we were designing Haskell again, I could imagine making it a strict language, but remorselessly pure, knowing how important it is now.
In what way? What design decisions would you change if you were to make Haskell again and make it strict?
Well, I don't know. So I suspect that then 10 years after that, I'd be saying, actually, there are really, there are ways in which being lazy was so convenient and helpful and elegant and beautiful. And maybe we should make it strict. Maybe we should make it lazy. I think the best thing to do is to say, it's not that one's better than the other. It's just that you've got to have a default of some kind. You should make your language as far as possible able to, accommodate both programming styles. And so I think Scala has quite a lot of support for laziness and iterators and so forth. And Haskell has quite a lot of support for strictness these days. And neither is perfect. I don't think we've yet seen a language which truly fluidly somehow makes laziness and strictness interoperate. It's a bit hard because if you've got a lazy thing, then any strict subcomputations, are then lazy. Well, or don't only get it. So I don't think there's a clear win to be had here. I certainly wouldn't say I definitely make Haskell strict if I was starting again.
One of the half-joked phrases that goes around in the Haskell community is to quote-unquote avoid success at all costs. Does it feel like a success that many ideas from Haskell have spread to other languages and become influential, and that way, even in Haskell itself, didn't become mainstream?
Well, the first thing to say is just to remind everybody that it's a kind of deliberate play on words in that it can be read two ways, right? It's read avoid success at all costs, by which it means avoid compromising the fundamental essence of the language in order to gain some kind of short-term payoff. But the second reading is avoid success at all costs, because if you become a successful language, then you have zillions of users who then become grumpy if you change the design or do something that isn't backward compatible, and that stops you being nimble. So now, to be fair, I think I still cleave absolutely to the avoid success at all costs, right? I think Haskell's distinguishing feature is that it clings very, very remorselessly to a few simple, elegant ideas like purity and laziness and type classes, and sort of says, okay, we're just not going to compromise on that, even if it's embarrassing and painful. But we haven't done very well on avoiding success. Because Haskell really is used by hundreds of thousands of programmers for their day jobs, and they really have started to become grumpy if we change the design in a non-backward compatible way. So I spend a lot of my time thinking about backward compatibility these days. But that's a price you pay for actually being useful.
Yes,
but to answer your original question is yes, Haskell is not a mainstream language, and it probably never will be, as in used by the majority of programmers in the way that, say, TypeScript or Python is, right? But it is quite an influential language, and I'm quite happy that Haskell has been a laboratory in which ideas have been born that have then, as it were, gone out into the world and influenced the rest of the world. I think it's a very good role for a programming language to play, very good role, and one that's very satisfying to me.
What would you wish some mainstream languages pick up from Haskell that they have not picked up already? I mean, Scala picked up quite a bunch of features from Haskell, but Scala is like, it's not that mainstream. It's borderline between niche and mainstream at this point. What would you think it would be a good idea for mainstream languages like the Pythons and the TypeScripts and the Javas to pick up from Haskell that you think would make them more powerful languages, more powerful languages without sacrificing what make them popular and productive?
High-kinded type variables, the ability to abstract. I mean, it just is seismic. I'm astonished that people don't pay more attention to it. Right?
That would be very interesting because Martin Odersky himself, the creator of Scala, is or has been on the fence for a couple of years about having added higher kinded types to Scala.
Yep.
Because it introduced a whole bunch of new complexities in the Scala compiler, and that comes with trade-offs in effort and so on and so forth. So,
and I'll tell you why.
Go ahead.
In fact, I had a whole talk about this called classes, Jim, but not as we know them. And the thesis of this talk was as follows. Well, actually, let me back up a bit and say the reason I think the reason that higher kinded type variables introduce such a lot of complexity is because they interact with other language features, particularly subtyping. So when is list of T a subtype of T? Sorry, when is list of T a subtype of list of S? Well,
this is the variance question, right?
Yes, exactly. Right. So you've got to worry about, is the type constructor covariant or contravariant?
Yes.
Right, or invariant. Now, what if the type constructor is a type variable? Well, now you have to say for all covariant M, blah, 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 or possibly for all contravariant M, blah, blah, blah. Right? And it's not long before you want variance polymorphism. You want to say for all variance V and V variant M, blah, blah, blah. Right? So you begin to drag in a lot of complexity through the door like this. So variance, which comes from subtyping. So Haskell does not have this problem at all. Why not? Because Haskell does not have subtyping. Why not? Because parametric polymorphism and type inference and subtyping, particularly higher kinded type variables, are sort of in tension with each other. It's very hard to combine them well. And so Haskell, we say, we will not do subtyping. That gives up something. But the thing is that, so why? But I want to suggest that, and this is this talk that I think I gave 20 years ago was trying to suggest this, to say the initial selling point for object-oriented programming was subtyping, right? So a vehicle, is a subtype of an object, and a car is a subtype of a vehicle, and a voxel is a subtype of a car.
Like there is a relationship.
There's a relationship between them. Then it's this subtype relationship. Moreover, you get polymorphism. So any function that works on vehicles will work on cars and work on voxels, right? So you get polymorphism through subtyping. By polymorphism, I mean one piece of code that works on arguments of different type. Now, parametric polymorphism also gives you polymorphism, right? One bit of code that operates our arguments of different type. We talked about reverse quite a bit in this conversation already. Right, so now we've got two different ways of getting polymorphism, through subtyping or through parametric polymorphism, right? Now, the subtyping world, the object-oriented languages, initially did not have generics. It got polymorphism through subtyping. And then they found, man, we really like those generics. So we'll have subtyping and parametric polymorphism. Right? And the interaction is somewhat complicated. Now, Haskell, we just had parametric polymorphism, no subtyping. And actually, you can get, I think, about 99% of the goodness that way. So the thesis of my talk, which was, object-oriented programmers of the world, now that we have now we've really explored the outer boundaries of parametric polymorphism, we no longer need the scaffolding of subtyping. We should get rid of it. Now, I'm oversimplifying, right? Because there's It's not just history and culture. There are good things about subtyping, but I think it's a very good conversation to have, because when you put all of these things together, you do get complexity. And that's what Martin is speaking about, the complexity of putting everything together. So I would say a defining characteristic of Haskell at the moment is no subtyping. Sometimes I regret it, it has a cost to it, but mostly I just rejoice.
Are there any underrated programming languages other than Haskell at the moment of this recording, in your opinion?
Underrated programming languages. There's lots of interesting stuff going on with effect systems at the moment. And so OCaml is being adopting effect systems in a big way. But Coca, Dan Lyon's language, has been a little laboratory for exploring effect systems, pretty interesting. And also a language called Granule, which is more of a research project for Dominic Orchard and his friends. So I don't think the world of algebraic effects has settled down yet into a state in which, a state of consensus. But so I don't know about underrated. Certainly, what's the word? Interesting. These languages that are
I think you can
effect
exchange
systems.
the terms for this particular question, and I think the question was satisfyingly answered. There's certainly effect systems baked into the existing languages, more like libraries and toolkits, like the effect systems in Scala, like Cat's Effect, Zio, Kio, and so on and so forth. There is the effect TS library in TypeScript, which is a port of the Scala Zio library within TypeScript. And there's certainly effect systems baked into other languages like Flix or Effect with a K. So there is certainly an exploration there, and
that's right. It's a zoo. It's a whole complicated design space at the moment.
So I take it that effect systems are your particular point of interest with regards to.
Well, as far as when I said interesting language, that would be one patch of territory that I think is being interestingly explored. But it's a bit complicated. I don't think I have a good visceral understanding of the world of effect systems. I think Martin is all by himself with a few colleagues exploring a very interesting piece of design space in type systems. He has a whole story about effects and capabilities and security, and the sort of path-dependent types that Scala has. So Scala has, under Martin's leadership, has some really very unique characteristics that I think are. So I think Scala is an underrated language in that sense, underrated by the research community. I think
Yes.
there are ideas in there that I would like to see more widely discussed and understood and, distilled, if you like, into forms. But Scala's a big ball of wax, right? So, and Martin has done made serious attempts to distill it himself in this little core calculus called DOT, the dependent object types. And I don't quite know why that hasn't caught fire as much as I would like to see in the research community. So underrated in that sense, I think.
Awesome. How is Verse coming along?
Astonishingly, I've been working for Epic for 4 years now on Verse. So my boss is Tim Sweeney. He's the chief executive and founder of Epic, and he's a sort of uber nerd, right? He wrote the first version of the Unreal Engine, right, which is Epic's core piece of intellectual property. He's an astonishingly good programmer, and he also has an extremely original brain, right? He thinks, he's designed Verse in his head over the last 2 decades, and he often says, Simon, it's just got to be like this. This is the way it has to be. And he'll then try to explain why. And I say, Tim, I didn't really understand that. Then 6 months later, I'll think, oh, now I understood what Tim meant. So he's in my mind, he's a bit. He's like people who can sort of multiply 20-digit numbers in their head and just tell you the answer. They can't tell you how they do it. They just know that that's the answer, and it jolly well is. Now, so Tim has extremely original and set of design choices and ideas that I'm still trying to get my head around, even after all this time. I've actually committed to give a series of lectures later this year at the Oregon Programming Languages Summer School about verse, which I'm going to try and unpack some of this stuff. So I would say that I'm still coming to grips with what is the essence of verse? What is the essence of verse? I thought it was, it's just an unusual functional logic language, and we wrote a paper about that a couple of years ago. But there's a lot more to it than that. It's a language in which patterns and expressions are the same thing. So usually in Haskell, we say lambda pattern dot expression, and patterns are just a different kind of thing than expression, right? They, an expression, if you give it the values of its free variables, it will produce a single value. Patterns, if you give it a single value, it will produce values for the bound variables of the pattern. They're kind of dual to each other. In verse, there is only one thing called expression that can function both as a pattern and as both as a pattern that is a value producer, a binding producer, and as an expression that is a value producer given. So I didn't think you could do that, but that's what happens in verse. In verse, types and terms are the same thing. So let's see. The integer type is simply a function, just an ordinary function. It's a high order. You can pass it as an argument. You can return it as a result. It's just a function. Int is a function that takes any value. If the value is not an integer, it fails. And by fail, I mean like return nothing in the maybe monad, right? It's not a wrong thing. Or it succeeds and is the identity function. It just returns the integer. Now, I could define the type nat to be a function that takes any input. So essentially it's sort of lambda x, int of x, so check that it is an int, semicolon x bigger than 0. So it's a user-defined function nat that takes an input, checks that it's an integer, checks that it's bigger than 0, and returns it. That's the type nat. I can define, the type of even numbers, or the type of numbers that are even and between 7 and 250. So, types are just functions. There is no difference between them. Now, the question then is, could you define a type checker for such a thing? And the answer is yes, but of course, some of the time the type checker is going to have to give up and saying, well, this is a bit complicated. I can't figure out whether the type's always going to be satisfied at runtime. But your program has a perfectly good meaning. It's just a question of whether the type checker can be sure that you're not going to get any runtime failures. And there are a bunch of other unusual things about verse. It's a functional logic language. There's a nice duality between choice and tuples. So it has a very strange denotational semantics. On and on. It's very far from the center of gravity of normal programming languages.
Sounds like it.
And
does it rely on different mathematical foundations at the core than Haskell?
Not really. We're still trying to use the same fundamental techniques of, how you might do, say, give a semantics for language, an operational semantics, a denotational semantics. But the operational semantics and denotational semantics look very different. Yes, the same basic tools. Tim is very ambitious for verse, though. He wants it to be the language of mathematics. He wants you to, to be able to write proofs as programs and write mathematical proofs in verse. So very ambitious indeed.
I'm going to leave a bookmark for that because I want to tie it to AI. But I wanted to ask about the class of problems that you believe the current structure of verse should make easier to solve than the languages that are currently being used in games, like the C# and whatnot.
Yeah, I don't have a good answer to that really. As in, I think mostly Epic could probably get. Epic doesn't for programming games. You could get, most of what you need by using an existing language. The real reason we're doing verse is because it's just the same reason as when I started functional programming. I think this is just the right way to write programs, right? And I think Tim thinks this is just the right way to write programs, and we're going to do it. I don't think I can point to a bit of verse and say, oh, this makes some game-related aspect of programming so much easier. It's just it makes programming. Well, what we have to find out is, does it make programming easier? But we can't answer that question until we have designed the language and have written some programs in it.
Do you think it will be able to make? I'm not sure how to phrase this because I wanted to phrase the question in terms of games. Will it be able to make games declaratively? How do you think about this?
Well, so I mean, verse, as I say, is ambitious. So in Haskell, we were felt free to say Haskell just is pure. That's the end of it. That's the hair shirt that we wear. We'll see where it takes us. But verse is not pure. Verse you can have verse programs can have side effects, and with verse we have to be very careful to keep those side effects in the right order. So it is a declarative language in the sense that the default of computation is that if you bring into scope a variable, it denotes a value. It does not denote a mutable location. Just as in Haskell, you can have the type of ref of int, right, which says I'm a mutable, I'm the type of mutable variables which I can side effect to change its value. So just like in Haskell, it's a different type. So int and ref of int are different types in verse. And mutating ref cells is, you have to be pretty explicit that you're doing it. But the default is that variables are bound to single immutable values, just like in Haskell or ML. But still, but unlike in Haskell, there's no monad in the type. So a function that may have effects, it doesn't have the result. It doesn't have a result type of IOInt. Instead, it declares its effects in a sort of annotation on the type. So you say function transacts. Takes an int and transacts and returns it. It's more like an effect on the arrow, if you like. So what does that mean? That means that for game programming, where you really do want to have an effect on the world, right? You've got multiple independent agents doing their thing and affecting some shared reality. That will all happen through side effects, but it'll happen through side effects mediated through transactional memory. So this is another thing that we learned in Haskell, is that transactional memory can really make communicating parallel shared memory processes work together much better. So, and the verse sort of runtime buys into transactional memory quite heavily.
Verse seems pretty complex and seems to have pretty involved semantics, which begs the question of, have you considered or what kind of design decisions went into verse that you think will make it easy to learn/teach, given the fact that this has the potential to be used by lots of game developers and stuff?
Yeah. Well, this is a bit of a hard question to answer, because you could ask the same question about Haskell. Right? Haskell is a pretty complicated language, right? When you in its full glory, it really is complicated, and yet, and also it's unfamiliar in its computational paradigm. Right? People are sort of instinctively think when they're programming, they think about do this and then do that, and Haskell doesn't have this do this and then do that thing. So, so in effect, Haskell is a bit of a thought experiment. What would happen if you took a language that really did buy into laziness and purity? Would it be teachable? Like, could programmers learn this? And the answer is, well, yes, they can. And but there's a whole forest of, and here's how you think about monads, and here's how you think about programming in Haskell. And I think people would probably differ about whether that's in the end is easier or harder. Maybe if Haskell was your first language, how would that differ? So I think all of this will be true about verse. I don't think I'm even close to a sense about whether what the verse learning curve will be once the language is settled, because the fact that Haskell is complicated doesn't affect you too much, provided you're not using the complicated bits. Right? The idea is it should be like a gentle slope. You're always programming in a language that makes sense to you, but every time you push the envelope, instead of there being a sort of hard barrier, a glass ceiling that says, no, you can't do that, it just says, oh, we can do that too. And I hope that the same will be true of verse. But honestly, it's an intellectual, adventure. It's a sort of like we're developing a rather new programming language. That means new way of thinking about programming, new way of learning about programming. We'll have to see whether it catches fire in the grand scheme of things.
How would you gauge success for a verse?
Well, same as for Haskell again. Does it serve as a laboratory that generates ideas that other people use? And secondly, do people actually use it? Now, Haskell been quite successful at the first and a bit successful at the second. Verse is a bit different because since it is the language in which game developers will program the Fortnite and Unreal ecosystem, right? So if you're going to write a game, you can write it in C++, very low level. You can write it in so-called, I think, blueprints. There's a very, very high level, not very expressive thing. So Verse is kind of like a scripting language in the middle that lets you write new games quickly. So, and it's been released already. So a version of Verse, which we, is available from Epic, has been for a couple of years. It's a shipping language. It's fairly conventional language with a type system that does involve subtyping. It's essentially it's ML sub. It has classes and structs and arrays and subtyping. So it's a somewhat conventional looking language, and it's available today. Now, the language that I've been describing, the sort of wildly ambitious one, is sort of way up in orbit somewhere, and then the shipping language is down here. We've got to try to join the two up. Now, that process will take a little while, but meanwhile, the practitioners are using the shipping language. And they don't get much choice if they want to program against the Unreal Engine and in the Fortnite ecosystem. That's what's on offer, and it's pretty good.
I want to go back to the bookmark that I left earlier, which is the fact that you are considering verse to be the sort of language of mathematics of probably theorem proving and adding a lot of guardrails and ensuring correctness and stuff. I mentioned earlier that I want to tie it into AI, and this is something that I wanted to discuss with you, because there's a huge conversation in the programming space around adding guardrails to programs or to programming languages. For example, in Scala, we have capabilities. There are programming languages like Lean, which do full mathematics and theorem proving so that AI code is safe. How do you think about LLM-generated code with this sort of context?
So two fairly obvious things. One is static type systems help a lot, right? They give LLMs a huge leverage, right? Because now it can iterate on until with all this agentic programming stuff, it can iterate until it gets the types right. Now, it's not true to say that every program that has correct types will do what you want, but it's a lot more true than if you're in an untyped language when it can not do what you want in a whole variety of new ways. So, in effect, the type system itself is some pretty good guardrails. I think they're just, fantastically helpful for vibe coding, if you like. So, thing number one. Thing number two, the amazing thing about theorem provers like Lean or ROC is that you can use LLMs to generate proofs or putative proofs, and then you can use Lean or ROC to check them. And it doesn't matter how bogus or how many bogus proofs the LLMs produce, because we have a completely independent, bulletproof way to check them. So if it claims to have proved a theorem, we can check whether it has proved the theorem. And if it has proved the theorem is true. It doesn't matter. We can't have hallucinations and, it sort of looked at some bad proof that somebody else wrote and did it a bad way. No. If it coughs up a proof and Lean accepts it, it's a proof. Right. That is fantastic. That means that completely obviates many of the the anxieties about generating code using LLMs, which is that they may generate code that looks plausible but actually doesn't work. And if you deploy that into your aeroplane, the aeroplane may crash, right? We just don't know. So But it's a bit of an extreme, right? Generating a mathematical proof that lean or rock can accept. That's pretty, that's good if you want to prove, some theorem of mathematics. But if you want to prove, does the code that runs my airplane, does it not make the airplane crash? Well, that's a bit hard, right? Partly because as a specification, airplane should not crash isn't really one you can write, right? So I suppose that then gets into what do we even mean by saying that this software is safe, right? Now, or verified. People are often sloppy about saying this is fully verified software, or that's our goal. Our goal is to fully verify this piece of code. Nobody ever can do that, because what you always mean is, I've verified that it meets some specification. So you've got to answer, where did that specification come from? How did you know that the specification is right? And even if the software does meet the specification, does that actually mean it's fit for the purpose? So for the airplane, well, actually, back up a step. What in practice we almost always mean is this piece of software has some properties. Like you might say, the airplane software will never put the left flap down and the rudder to the right at the same time. That's impossible, right? So that is a property. And you might then, or for a sorting algorithm, you might say the output of the sorting algorithm has the same length as the input. It's not a complete specification. It's just a property. You might say the output is in ascending order. That also is not a complete specification. It is a property. If you have enough properties, you might say we have a full specification, but even that, as I say, is very clear. So for me, verification is always about proving some properties. And the more sophisticated your language and its type system, the more sophisticated the properties you might prove. So in verse, for example, you might really be able to prove to write down and then, perhaps prove some quite sophisticated properties because the language is very expressive. But that's the name of the game. So this links it all back to property-based testing. I'm a big fan of property-based testing. And to me, that's just a runtime version of verification, right? All we do is property-based. We either do property-based verification or we do property-based testing, one or the other, right? All verification is really property-based verification, whatever people say. It's just they think this one property is enough. So I would like to say, do property-based testing and try to verify all of those properties. Maybe if you have 20 properties that you say your program has in your PBT library, you can perhaps verify 10 of them, and then you don't need to ever test them again. Right? The other 10, that was harder to verify, so we still better test them. And meanwhile, we better work on our verification technology.
How would
So that was a rather long answer to your question.
I love that because it's very nuanced and it points to gaps in the conversation. The one liner is we need to make a LLM generated code safe, but what does that mean? How to
exactly? What does it mean? We haven't got a clue. It's just not. It's not a meaningful question to ask. You've got to be much more precise about what you mean by safe.
How would an ideal programming language look like to allow the productivity that LLMs promise, and yet have the properties that you're describing? So the ability to verify that a specification, which has been written somewhat formally, holds true. So how do you design a language that meets those criteria? And what are some of the features that you would focus on if you were tasked with such a thing?
Well, in a way, I'm hesitating because the remarkable thing about LLMs is they're spookily good. They're just spookily good, right? So they can do things that are far beyond what we could hope to reasonably verify at the moment. That's why. So what does that mean? I would like to have a language in which I could do rich property-based testing, and that means I need a language in which I can write down pretty sophisticated properties. Sometimes specifications are written in a language different to the programming language. So verse specifications would really be written in verse, in lean. They're written in lean, but say in Haskell, we got this other thing called liquid Haskell, which is the newest thing we have to verification system for Haskell. Liquid Haskell is really good, but it uses so-called refinement types, which are not Haskell, right? So it uses a richer language to describe the specifications. So ideally, you'd see all that unified in one thing. I don't have a single picture in mind for what that would look like. I think I'm a little anxious that the whole AI thing, although it's so spookily good, will mean that we increasingly get code that's running in critical systems that really nobody has ever reviewed.
That's my scare as well.
And I don't quite know what to do about that, but just saying let's formally verify it instead isn't an answer, because we don't have the technology that can formally verify these, enormous software stacks. And software is enormous.
I wanted to touch on teaching for a moment, because you have founded CAS. How would you teach a young kid, like 8 to 10-year-old, let's say, to program in a real language? What would you focus on? What are some computer science that you think are vital for for children to understand, especially in these years where they can very easily ask an LLM, they can produce some code, they can very easily convince them that the code is right, and so on and so forth? What would you focus on? What kind of fundamentals would you consider critically important?
So although I've expressed a worry, I also express some joy. My son recently, he plays a lot of Minecraft, and he was trying to Google around to look for Minecraft script, and he said, "Dad," he said, "I found a button that said dive deeper with AI." So I pressed it, and it turned out he got into a conversation with Gemini that started coughing up Minecraft scripts. That meant that he could sort of copy paste into his project, and they sort of didn't work. So he started a dialogue with Gemini, which actually succeeded in refining and improving his script to the point where it did work. And he found this quite empowering, quite empowering. And he's sort of pretty enthusiastic about it. So in a way, that's led him into a world of programming which he might not have otherwise have gotten into at all. He might have just bounced off it. I think it's worth thinking about, analogizing with natural science. So in natural science, we teach children about atoms, say, even about protons and neutrons and electrons, when there's no conceivable reason that a child or even an adult would ever directly, they're never going to directly see or manipulate atoms. So why do we teach them about atoms? Because they give you a systematic and fundamentally true way to understand the complicated world that surrounds us, right? So it's not that you directly use them, but they sort of underpin your knowledge of everything: heat, velocity, friction, combustion, internal combustion engines, climate, global warming. All of it is underpinned in the end by our knowledge that the world is made up of atoms. So in the same way, even though AI systems may be able to cough up code that sort of works, I don't want this to be like a magician. Like if you utter the right spells for the magician, he might cough up a program that works, right, or do something valuable for you. But then you're dependent on the magician. You're utterly dependent on the magician. And if you cast the spell the wrong way, he doesn't do it, or maybe he turns, your sister into a frog rather than into giving her sort of, the extra brooch that she wanted. So got to, you're sort of you're disempowered if it's just casting spells, right? So for me, then, I think an important part of education is giving young people knowledge about some of the underlying fundamentals that then inform and give them a well-grounded understanding of all the technology that's sitting on top of. So for me, that's bits and programming. So last year I gave a talk intended for a lay audience called Bits with Soul. It's very Googleable as a title. It's a 1-hour lecture that I went all the way from the binary number system through to AI in 1 hour for an audience that included everything from 14-year-olds to professors of quantum mechanics. It was quite a tough audience. But I think it's an important part of education that children should have some understanding that everything is made of bits, sound, music, AI, everything is bits, and that they should have some understanding about writing programs that work step by step, and some understanding also about how we can learn from data using neural networks. So I'd like them to understand at some level how a two-neuron neural network works, and they should be able to see it learning. And then you can say with truth that ChatGPT is simply a trillion of these things stuck together. The only real difference is scale. Yes, there's tons of ingenuity and there's thousands of papers and cleverness and transformer models and so forth, but the raw material is still the same. It's a bit like saying atoms underneath everything. So there's a rather long answer to your question again, but I think every young person deserves to have some kind of underpinning, basic understanding about bits and programming. And neural networks at a very elementary level, and then should have some understanding about how to use in a thoughtful, critical way all the systems that surround us.
How about for a junior programmer about to enter the workforce? Because a difficult conversation in the software industry is that juniors are less and less hireable because a senior can just prompt like 3 LLMs and just do all the work. How would you advise a junior that is just entering the workforce in this AI-enabled era to train strong foundations and good taste, like tasteful approach and tasteful design, tasteful abstractions, while using AI? Do you have any thoughts on that?
Yeah, I don't really know. Some of these things are in a very rapid flux. Right, a year ago, you wouldn't be asking this question because Claude didn't exist. Really, the LLMs were not good enough to produce even entry-level programmer code. But now they are. There's been a qualitative shift in the last 12 months, I think. And so it's hard to know what to say, given that things are changing so rapidly. I do worry that if we simply stop hiring junior programmers, we soon won't have any senior programmers either. Because how did the senior programmers become senior? They started life as junior. So I think in the end, companies are going to have to figure out how to grow their developer talent so they get those senior programmers who are able to review what LLMs produce. And I think I'm sure they will figure that out. And in the end, it will be a power tool that lets us be more productive. But it does seem that we're in the middle of a pretty sharp discontinuity at the moment, in which, and I'm already afraid that there'll be some casualties. That is, people who are graduating or early stage in their career who might very reasonably have expected to get a job easily now find it hard. I suppose the obvious things like get good at using LLMs yourself, right? But I don't think I've got anything to say that isn't being said, in a much better informed way by lots of other people.
What about the reverse? If you're a senior developer now, you're empowered by AI. You can use AI for vibe coding, power coding, name it however you want, and the proportion to which you're using AI to generate your code. How would you advise a senior developer to use these LLMs without atrophying skills and some of the critical foundational thinking that became part of what makes somebody a senior developer?
Oh, I think that's probably easier because it's not just a question of you give it a prompt and it spits out some code and you paste it into your project and you're done. There's a elaborate feedback loop through these agentic programming things in which you're constantly making, looking at the code that's produced and wondering, is that how I want it? And maybe you can even be using it to help you make designs. My colleague Anil Madhavapedi says that one of the best things that he's using AI for is saying, look, write me the module signatures for a module that does this kind of thing. That is, the module signature is like the type of the module. So don't write me the code, don't write me the implementation, write me its type. That is, and this is the language in which is another benefit of static type systems. It's a design language, right? It lets you describe your design before you've written a line of code. He's using it a lot for that. So I think there's lots of stuff that senior developers will be able to use AI for in a productive and conversational way. And producing documentation and producing test cases. I mean, they know these things are important.
Do you have any book recommendations for programmers that you think are still relevant now? I mean, there are many books that have been timeless across the decades. Do you have any particular favorite books that you would recommend that you think, and for example, any programmer should know or should have read? Another way of phrasing this question would be, have you gifted any programming books to other programmers, and has there been a recurrent pattern?
It's not really. I mean, the only thing that you're triggering off in my mind is I remember reading Chris Okasaki's book about functional data structures. It was a real eye-opener. That was about immutable data structures, which nevertheless do things that you might think could only be done as side effects, like double-ended queues. And he showed that you could implement them using amortized complexity, amortized linear complexity. That was a real eye-opener, right? So knowing that a class of solutions is possible is really helpful, and it's a short book. I also remember reading Aho, Hopcroft, and Ullman. This is a 40-year-old book about classic graph algorithms and the related algorithms, and some of Don Knuth's books. That's still great. The whole I'm just showing my age. The other book I remember well is the sort of does P equals NP book. Now, what's it called? It's a classic book about algorithmic complexity, but it's a not very long paperback. It gives you a clear idea of why exponential complexity matters and how you might reduce one exponential. Beginning with G. Why am I blanking on its title? I'm sure you'll find it from the show notes. I'm sure you'll put it in the show. Absolutely classic book from 40 years ago, but not long, again, and still as relevant now as it ever was. For practitioners, I'm not a programming practitioner, right? I've never worked for a large software engineering outfit that's producing millions of lines of code. So, I worked for Microsoft, but I worked very much in research. But I remember looking at various Microsoft software developer authored books like writing robust code or something, and thinking, oh, that looks very plausible. That looks good, but it's not rooted in my own experience. And they're in contrast are very long, right? Because they're describing software design practices. So no, sorry, not very good answer to a question there.
We have enough show notes for this answer. Has there been? Do you think that in your career you've had a habit that you've stuck around with for a long time that you believe has compounded your skills and your results over time?
I've remembered who it was. Gary and Johnson. Garey and Johnson. That's the book about algorithmic complexity.
Mm-hmm.
Sorry, ask your question once again.
Do you have a habit that compounded your skills over time in your career?
No. What about a habit? I think I have been privileged to be able to stick to a few simple ideas and follow them through, right? So I've been lucky enough that I've been able to say functional programming is what I want to do, and purity is it. I'm just going to pursue that. And as an academic, you get to do that. If you're working for a company, you just have to deliver the product the company wants. Then if you can use functional programming for it, great. And if you can't, well, too bad, right? So I feel that, so it's been a privilege, but it's also been of the original Haskell committee, for example, I'm really the only one who's still working on that same language and that same compiler. But I've sort of persistently stuck to that one idea: purity, laziness, static types. So I suppose I've been persistent, and that doesn't mean, but always thought that's persistence, not because I think this is better than any other approach, right? There are lots of clever people in the world and they all have interesting approaches, but because it's an approach that is sufficiently rich, deep, interesting, and fascinating that it's worth somebody devoting full-time attention to in a sustained way. So I suppose I've tried to do that. Another thing that is not exactly a habit, but it has turned out that if I look at my website and look at the sort of hit rate on different pages, the pages that get by far the most hits, like by 100 times as many as on any of my papers on functional programming, are the ones about how to write a paper and how to give a talk. So I have been able to distill out something about communication skills that have seemed to be useful to other people, and have certainly been useful to me.
You're certainly useful to me, and you're certainly useful to the audience listening to this conversation, and that definitely shows. You're a very articulate speaker, and you have a, I would not just say talent, but a well-crafted skill over the years of distilling very complicated things into very few words that are understandable on the other side, and I have to thank you for that.
Oh, that's good. That's good. That distilling can be frustrating. One of the things about verse is I'm finding frustrating at the moment. I keep thinking, Simon, if only you were a bit smarter, you could figure this out. I'm really trying to distill out a way to explain verse that is comprehensible to me, let alone to everybody else. So I'm sort of relentlessly driving towards simplicity and only accepting complexity when nothing else will do.
Well,
that's a habit, if you like. That is a habit, but it's an expensive one.
But it's worth keeping, I think. And it's of tremendous value because without that, no matter how clever your product is, no matter how smart your theorem is, without these communication skills, the value, or at least the perceived value of these ideas and products will probably be, I don't know, multiples lower, So
yeah,
I think it's a valuable trait.
It's a good habit, but it's an expensive one, right? So, and as I say again, I take it as a privilege, not as a right, that I'm allowed to do that.
And we appreciate.
And many people are not. Many people, just got to get it done, right? You've got to sellotape, string if need be, but it's got to, the airplane has to fly, and it has to fly by Thursday, please.
And it has to fly well, because otherwise, if it crashes, we got a problem.
Yeah, that's right.
And I think this is a good place to wrap up. Simon, I want to be respectful of your time, and I wanted to thank you for making the time for this conversation. I'm going to put links to everything that we've discussed in the description. And I wanted to ask if you have any sort of ideas or things that you would like to say to my audience before we wrap up. Remember, the audience is mostly functional programmers at the time that we're recording this.
So I've often said in the past that when the granite of imperative programming when the limestone of imperative programming has worn away, the granite of functional programming will be revealed underneath. I still think that functional programming has a has a kind of long-term durability for the future. It's on a long, slow burn. I think it will continue to be influential. So I think the whole declarative mindset, which is something you described your audience as having, that is really valuable. So you should sort of cling on to that. And there's a paper by Pat Helland, and its title is Immutability Changes Everything, which is the most brilliant title because it's a play on words, but it's also a profound truth. Because, of course, will lean on that in the context of programming language design. But his point is that applies to log structured file systems and databases and caching in operating systems in many, many places. So it's a great title. And so I think if your audience goes away and think immutability changes everything, I can't always do that. Sometimes I'm stuck with mutability, but I need to keep Keep it in its box. Don't let it escape and pollute the world. Immutability changes my entire outlook on the world. And that's the granite of functional programming showing through. That's quite inspiring, actually. It's quite inspiring that something so simple has such profound consequences. I find that very intellectually and practically satisfying.
Immutability changes everything. This is a sort of phrase that would be worth putting on a billboard in front of
it would,
many
yeah.
programmers.
But credit to Pat Helland. It's not my phrase. It's a very good one. He's a genius. Yeah, that's right.
Simon, it's been a pleasure. Thank you so much for making the time.
It's a pleasure. Yeah. Thanks a lot, Daniel.